Hello and welcome to the Combined Science Aiming for the Top Grades Walking Talking Mock. So I'm going to go through this paper today and hopefully you'll be able to see where the marks come from and the thinking behind it for any of those questions that perhaps you weren't so clear on. So starting with question one, this is easily one of the biggest questions of the paper, so we're going to spend a little bit of time on this one. This is to do with forces acting on an apple, and there's some key information in the question that we need to make sure we are paying good attention to. So the first thing is the fact that this apple is a stationary apple, and we're also told that X is marking the centre of mass of this apple. The first part of this question then is asking us to draw two arrows on that figure to show the forces acting on the apple. Now, whenever we've got a diagram where we're drawing force arrows, we call those free body diagrams, and it's very important that in free body diagrams we are drawing the forces away from the object and they originate at the centre of mass of the object. So we must be drawing our arrows from the X point on the apple, and it's a stationary apple. So that gives us a clue as to the relative sizes of the forces on this apple. If it's stationary, that means that the overall forces on this apple are balanced. So that means the forces in one direction are equaled out by the forces in another direction. Now on this apple, if we're focusing on just keeping it as a simple example as possible, we'll be talking about the weight pulling it down. So there's going to be an arrow downwards. So I'm going to draw that in here. And apologies for being a bit wobbly. You would obviously be using a ruler and a pencil on your paper. And then there would therefore have to be a counteracting force upwards, which would be effectively the tension force in the stem pulling up. And so I'm going to draw an arrow upward to represent that. And again, that would need to be straight. Now the key thing about it is if these two forces are meaning the apple is stationary, like I said, that means they would have to be equal in size. And so with a free body diagram, that means you have to make sure that you are drawing those arrows to the same length as each other. Now there's no need to have a particular scale here. You don't have to draw a particular size force for those arrows, but it is very important the two arrows are equal in length to each other. So using a ruler to make sure they are the same length and really make it as millimetre perfect as possible, going to mean that you're going to not drop either of those marks. So carrying further through the question, we've now got an example of a fairly taxing multiple equation calculation, and this is why it would be found on an example of a higher tier paper like the one that we've got here. So there's some key information in the question I'm going to highlight in order that it helps to direct our thinking for what calculations we need to be performing with that data. So we've been told that this apple takes half a second to fall to the ground. We've been told the initial velocity is 0. And that links back to the earlier part of the question. It's stationary, it's just hanging from the tree. We've been told that the acceleration downwards due to gravity is 9.8 meters per second squared. And then we're being asked to calculate the distance that this apple is falling to the ground. It then clearly tells us to use the physics equation sheet. So in your exams, in your summer exams this year, you are going to get an equation sheet that will look just like the one that hopefully you can see on the screen now. And hopefully you've also been given a printed copy by your teachers. Now it's very important that you don't sort of fall into the trap of thinking, oh, I've got all my equations on the sheet, I don't need to worry about thinking about any of them, revising any of them, practicing with any of them at all. All I need to be able to do in the exam is look at the sheet, put in the numbers. And that would be a mistake that is going to likely catch you out. So you are not going to be, as you can see from this question, necessarily directly told which equation to use. So you need to therefore have a bit of skill about using the equation sheet appropriately. The other thing you'll notice when I go back to the equation sheet is you're not given units. So you need to know what the standard units are for measurements. So when it comes to selecting the appropriate equation, it's about looking at what information is given to you in the question that will help you to know what the appropriate equation is. So I can see we're given a time in seconds, we're given an initial velocity in meters per second, an acceleration in meters per second squared, and we're asked to calculate the distance. So if I go back to the equation sheet, I'm looking for which equation, or in this case equations, are going to be utilizing those different measurements and then being able to put the numbers into it. And on this first page, from glancing at it, I can immediately see that there are no equations on there that use those different measurements. If I continue on to the second page, I can now see that it's the two equations just here, which hopefully I've highlighted, which is acceleration is change in velocity divided by time, and final velocity squared minus initial velocity squared equals 2 times acceleration times distance. Now the reason we need to be able to use, or we have to use, two equations is because of the fact that the equation we want to use at the end, which is the second of those equations that has the distance in, at the moment we do know the acceleration, we do know the initial velocity, but we don't know either the final velocity or the distance. And you cannot complete an equation with two unknowns. So we therefore need to work out what is the final velocity, and that's why we need to use the equation above it to work that out. So I'm going to walk you through how this works and how we can link these two equations together. So I just said the first equation we're going to use is going to be this one. Acceleration is equal to change in velocity divided by time. Now the reason we're going to do that is if I put this out in a slightly more fuller example, the way we calculate change in velocity is we work out what's the final velocity, what was the initial velocity, the difference between those two things, and then we can divide it by the time. So that's the kind of the full version of that equation. That's what I mean by you need to understand a bit more than just accepting that you've got the equation sheet and relying on it, but actually what does it really mean? So now I can start to put some of the numbers in. So my acceleration that's given to us is 9.8 meters per second squared. Our final velocity is unknown, so I'm just going to type in final velocity. Our initial velocity is 0, and our time is 0.5 seconds. So, continuing to work this out, 9.8 is equal to, well, final velocity minus 0 is just final velocity. And then divided by 0.5 to therefore finish working out this equation. To get rid of the divided by 0.5 on the right hand side of the equation, we have to do the inverse operation and times by a half, and if we do that to that side we have to do the same to the other side. So this ends up being 9.8 times 0.5 equals the final velocity, and that is equal to 4.9 meters per second, because that's the unit for velocity. So we now have our final velocity. And if I just pop back to the equation sheet again, we're now going to put this number into our second equation here. Final velocity squared minus initial velocity squared equals 2 times acceleration times distance. So let's type it out. Final velocity squared. You have to accept that it's a 2, I'm afraid. It's difficult to do the superscript on this computer at the moment. Minus initial velocity squared equals 2 times acceleration times distance. So the final velocity squared is 4.9 squared. 4.9 times 4.9. Work that in a minute. I'm just going to put it in brackets. And actually that's an important thing. I'm just going to highlight that, seeing as I've mentioned it. Can you see how we've got both of these numbers are in brackets here? Just making sure that you make certain that the thing you're squaring is the final and the initial velocity separately. You're not doing final minus initial and then squaring that whole thing. So that's just worth noting there. So in fact, let's just go back and add those brackets in to our earlier example, just like that. So we've got 4.9 squared, which I just typed out as 4.9 times 4.9, minus 0 times 0. Hopefully we can tell that 0 times 0 is nothing, but just for the sake of being as clear as possible, I'll put it in there. And this is equal to 2 times 9.8 times our unknown distance. So I'm going to carry on with that working out. I don't know my 4.9 times table, as much as I'd love to claim to be fantastic at maths. So if I get out my calculator and I do 4.9 times 4.9, I've got 24.01. So 24.01 minus 0, because 0 times 0 is 0, equals 2 lots of 9.8. I can do that in my head, which is 19.6 times the distance. And now I need to do again, just like I did before, I need to effectively get the distance on its own. Now distance is being times by a number. So instead of what we did last time, which was the multiply, we have to do the divide. So the answer is going to be 24.01 divided by 19.6 is going to be our distance, And if I go back to my earlier calculation and do 24.01 divided by 19.6, I've got 1.225 meters, and that would get you the full 6 marks for doing that. If you'd rounded it to 1.23, that would be fine. 1.2 would also be fine. The one thing to watch out for is don't make the mistake of doing 1.22. If you're ever going to either a certain number of significant figures or decimal points, you need to make sure you always look at the next number to decide if it needs to be rounded up or down. And in this case, it's a 5, so that's a round up. It is worth noting that if you were to do your earlier calculation incorrectly, so for example, let's say you got the wrong number here and you didn't calculate it as being 4.9, if you use the incorrect number correctly in the subsequent calculation, you can still get credit for the second section of marks there. So it's basically, you could still get about half the marks for this question. So don't give up on these questions. Show you're working. It's really important because there's a lot of marks that can still be gained even if you make a mistake earlier. If you just show the distance answer and it's wrong, 0 marks. So please don't just be lazy and just do it all on the calculator, get a mistake in there and get no marks. It'd be a terrible shame. All right, then the final part of this question is saying that in part B it was assumed the acceleration was a constant 9.8 meters per second squared. Evaluate this assumption. So the first thing is just to remind ourselves of the context of the situation. So we are talking about an apple that was hanging from a tree, has then broken off of that tree and is falling to the ground. Now when we're talking about falling objects, the two key forces, as we can see, similar to those that are labelled on the diagram, we're talking about a downwards force of weight, and the upward force on a falling object we're talking about is air resistance. So in the picture at the moment, because the apple is hanging from the tree, there is no air resistance acting on it. That's the tension in the stem. But if it were to fall, there would start to be some air resistance acting on the apple. Now that air resistance is not a constant amount. The weight pulling it downwards will always be a constant amount because that's dependent on the mass of the apple and the strength of gravity. And the strength of gravity on Earth is a fixed number of 9.8 or 9.81. And so actually the thing that's going to affect the acceleration of that apple is going to be how the air resistance changes. And with a falling apple, as it starts to accelerate downwards more, it's going to then start to have the air resistance build up on it. And so the air resistance starts getting larger as the apple accelerates downwards. And it's just the same idea. The context that you all have seen this before is the idea of a parachutist doing a skydive. So just to show you this, hopefully you will have seen plenty of examples of diagrams rather like this one on the screen at the moment, whereby as you go and first jump out of a plane, the air resistance will be very small because the parachutist is barely moving, their weight is the larger force, so they accelerate downwards. Eventually, as the weight continues to pull them down, their air resistance gets larger. You get to a point where the forces are balanced, that's a constant speed then. And this is the knowledge that we're going to be applying to the context here of the apple. So I go back to this question then. It says we need to evaluate if it's true that the acceleration was a constant 9.8 meters per second squared. So we're going to consider there are two possible approaches to this. You can either talk about the evaluation side of it that is saying yes it is true, or you can argue no it's not. I'm going to start with the no it's not because I think that is the easier link to make. So with that in mind, seeing as I've mentioned it, we're going to start with this. As the apple falls, the air resistance increases. So if the air resistance acting up on the apple is increasing, this means what we call the resultant force on the apple starts to decrease. And just to draw a couple of terrible drawings, linking back to that skydiver, if there's our apple, at the beginning, its weight going downwards might just have a small air resistance upwards. So I'll try and draw a small arrow there. However, as the apple accelerates more and more, it still is going to have the same weight going downwards, but now the air resistance upwards is starting to get bigger as the apple gets faster. So if the air resistance is getting larger, this resultant force, which is the overall force on the apple, starts to decrease. So it still is downwards, but it's not as big as it was. If there's less of a resultant force downwards, this means the acceleration downwards is lower. So I'm just going to add in fact, just because it helps, the resultant force downwards decreases. So the acceleration will decrease. And this means the assumption is incorrect, as acceleration is not constant. So that's the first way you can think about it, is you can argue the reasons as to why it's not correct. So the other way you can do it is you can argue that it is correct. And this requires us to momentarily look back at our answer to part B as to what the distance was that the apple fell. Now this apple fell only 1.2 meters. That is not very far. In 1.2 meters, the amount of air resistance that's going to be able to start to build up on act on the apple is very small compared to the example we were mentioning to do with a skydiver. So this is where we are going to be effectively arguing that because of the small distance, this building up of the air resistance is so negligible as to not have an effect. So therefore, the other argument is the apple only falls a short distance. Air resistance is negligible. I love that word. Basically, it means that it's very, very small. So the air resistance is negligible. The resultant force is constant. Therefore, acceleration is constant. And it is a good assumption. So those are the two different ways you could choose to approach that question. Both of them would be correct. The thing that you need to make sure you do is you're linking your justification clearly to the science behind it. All right then, well that was a big old question, but that's actually a huge chunk of the marks already done through. Question 2 here was just a 1 mark one, and this is just asking you what is the wavelength of the electromagnetic waves in the electromagnetic spectrum. And the key thing to remember about the electromagnetic spectrum is it covers a vast range of waves, from really, really, really long radio waves to incredibly short gamma rays. And this here is representing this in standard form, whereby the minus number means that it is that number divided by 10 that many times. The positive number means times by 10 that many times. And the one that shows that huge range from tiny, tiny things is this one here, 10 to the minus 15, which means divided by 10 15 times, and 10 to the 4 means times by 10 4 times. So we're talking about nanometers all the way up to effectively what's going to be that, well, 10 to the 4 is going to be tens of thousands of meters. So it's very, very, very long distances and very, very, very short distances that we are talking about here. Question number 3. So this is saying a student is investigating how the colour of the surface affects the amount of infrared radiation that is being absorbed. They've got some equipment whereby they've got a timer, a lamp that emits infrared radiation. We've got 2 flasks, a white one and a black one, and each flask has a thermometer inside of it. We've then got a simple method that the students used. They've poured water at 20 degrees into each flask. They've placed a bung and a thermometer into each flask. They've placed each flask in front of the infrared lamp, and they've measured the temperature every 30 seconds for 10 minutes. Now what we're being asked to do is explain 2 improvements. And this is really important. We're going to get marks for just 2 pairs here. So it's both what the improvement is and why that improvement needs to be made. And this requires us to look at their method and identify which things they have not done. And this is a combination of the written method as well as visually the equipment that you can see. And for me, the most obvious thing that I can see when I look at the equipment is that this flask and this flask are clearly very different in shape, and that is going to be a variable that should be being controlled. So the first thing would be that both flasks should be the same size and shape. And the reason is that if they're a different size and shape, this is going to affect the surface area of the flasks. And the surface area of the flask is going to have a big impact on how readily it emits the infrared radiation or absorbs the infrared radiation. And that's going to affect how quickly the temperature changes. So they should both be the same size and shape so that they have the same surface area. So that's the first one. The other one to me that stands out most is that they have talked about here in the method pouring water. Now they've told you the starting temperature of the water, which is great, but what they haven't done in any way is tell you the volume of water. And I'm going to really point that word out, volume. Don't say amount. So same volume of water in each flask. And again, that's because if you've got a larger volume of water or a smaller volume of water, that's going to affect the rate at which the temperature increases. So a larger volume is going to heat up more slowly, a smaller volume is going to heat up more quickly. Actually, I typed the word speed in there, but I corrected myself. Rate is a better word to use as the volume of the rate of temperature increase of the water. And you would only need 2 pairs, but I'll go through a third one anyway. So if we look here, the other thing that isn't made clear from the method, either from the picture or from the written method, is that they have just said to place each flask in front of the... Oh, sorry, the highlight isn't working. Hopefully it works now. No, oh well. So place each flask in front of the infrared lamp. What they haven't made clear, and again it isn't clear here from the diagram, is the distance. And the distance is going to be another factor that's going to affect it. So I won't type this one out, but the other thing you could say would be to have the flask the same distance from the infrared lamp, and that's so that the intensity of the infrared radiation on both flasks is the same. Alright then, we've now got some data from that experiment where we have got the time in seconds along the x-axis and the temperature in degrees Celsius on the y-axis, and we've got a graph or a line, sorry, on the graph showing the black flask and another line showing the white flask. We've now got to pull some data from this graph. Whenever we are pulling data from a graph, please use a ruler to make sure you are really accurately reading off both axes. If you try to do it by eye, it is very easy to accidentally go a square either side, and that will mean that you are no longer being accurate and you would not therefore be correct as to the masking. So the first part, it says after 100 seconds the temperature difference between the black and the white flask was blank degrees Celsius. So what you would do, and I'm not sure if I can do this very well unfortunately on here, but you would want to draw a completely straight line at 100 seconds going up. Again, I'm having to do this freehand with my mouse, which isn't easy. You can then see the white flask, and you'd then want to go directly horizontally across. So hopefully we are in agreement that that white flask at 100 seconds is at 24 degrees Celsius. Similarly, I would carry that on all the way up to the black flask. Now this one, actually, oh, I've drawn that a bit poorly. Let me just remove that most recent line. If we look, it isn't actually exactly in line with a square. It looks to me like it is directly between those two there. So this one is between 31 and 32, so therefore it would be 31.5. If this one was at 24, that means the difference between those two things would be 7.5. So 7.5. Now they will allow an answer of 8, but I think it is just worth being as exact as possible, and if we do look at that one, we can see that it isn't at 32, it's really at 31.5. It then says the temperature of the white flask stopped increasing. The temperature inside the black flask continued to increase for a further blank seconds. So exactly the same approach, but if we're looking for where it stopped increasing, we're looking at where the line goes to a horizontal line. So this time I'm going to go to the white flask here. I'm going to draw straight down. That one's nice and simple. So that's at 200 seconds. The black flask, again, be really exacting with this. It is no longer curved at this point here. Now, hopefully you can see if I keep drawing this down. Ooh, I've gone a bit wonky there, so I've gone back. Much better if I had a ruler. We can see that there is at 402 squares. Now our scale or axes scale on the left-hand axis and the y-axis was nice and simple. A square was 1 degree Celsius. Here on the y-axis, it's a bit more complex. We've got 5 squares between 400 and 500, therefore it's 2 squares, so that's 440 because each square is worth 20. So if it's 200 and it's 440, we're therefore at 240 is the difference. All right then. So it then says the initial rate of absorption of the infrared radiation by the black flask was greater than the initial rate of absorption by the white flask. How does figure 2 show this? It's as simple as just the steepness of the line, and the word we want to use there is the gradient. So the black flask has a steeper gradient, showing that the temperature is increasing more quickly at a higher rate than the white flask is. Okay, so I'm not going to type that one in because hopefully you can see that nice and clearly. And the last part here for this question, it says, why is the temperature of the water in the flasks increased? Explain why the temperature of the water in the flask increased and then became constant. So the reason why the temperature is going to change is to do with the relative absorption or emission of infrared radiation. So going back to the diagram of the setup here, the infrared lamp is going to obviously be putting the infrared, emitting the infrared radiation towards the black and the white flasks, and they will absorb some of that infrared radiation. They will, however, also emit their own infrared radiation into the surroundings. And it's the relative difference between the absorption and the emission of this infrared that causes the flasks to either heat up, cool down, or even stay the same temperature. So here, and again, I'm going to leave the graph, I think, on the screen just to help us with this question. If the question is asking us to explain why the temperature increased and then became constant, well, it's increasing at the beginning because the absorption of infrared is greater than the emission of infrared. So at the beginning, for both the black and the white flask, more infrared is being absorbed by the lamp than they're giving out. Over time, however, as they get hotter and hotter, they will start to emit more and more infrared radiation. And you eventually start to see that line start to plateau, and the temperature starts to increase more slowly where we've got the curve that's less steep, and eventually goes completely horizontal where the temperature is now constant because the rate of emission and the rate of absorption are equal. Now, if then the lamp were to be turned off and the flasks left, what you'd end up with happening is the flasks would start to lose temperature like this. And the reason they would lose temperature is because now they would be emitting at a greater rate than they are absorbing infrared radiation. And it's that difference in absorption and emission, that rate of energy transfer, that leads to the change in temperatures. All right then, almost there. So question number 4, we've got a diagram showing how light waves are going to refract when they pass from air into glass. Explain why the light refracts as it passes from air into glass. So something that's very helpful to use for this is a little bit of a mnemonic that Dr. Rose taught me, which is FAST, F-A-S-T. And this is that faster away, slower towards. So this is really helpful when it comes to understanding the reasons, not really understanding I suppose, but remembering what happens to waves as they move into or out of different mediums. And so here we've got light initially moving through air and then going into glass. Air, comparative to glass, is a lower density medium. So air is lower density, whereas in comparison, glass is higher density. Now what this means is that air is easier for the light waves to travel through, glass is harder for it to travel through. As we therefore have the light waves move from the air to the glass, they are going to slow down. So what's happening, I'll just add a couple of extra annotations to the diagram, is that at this point here, where this side of the light waves are hitting that boundary between air and glass, you can see that it is changing direction. The reason it changes direction is these waves are being slowed down by the higher density glass. And when they're slowed down, going back to that little mnemonic that Dr. Rose taught me, I'm going to split it down the middle. If they slow down, they go towards the normal. The normal is this imaginary 90-degree line that we can draw at the point that the wave is intersecting with the boundary between the two mediums. And that wave, instead of carrying on in its original direction, which would have been that way, has moved this way towards that normal. So it's slowed down, it's moved towards the normal. Now the rest of the light wave over here hadn't yet hit the boundary, so carried on at the same speed in the same direction. However, when it does eventually hit the boundary between the air and the glass, it will also slow down and then also move towards the normal. Alright then, on to the last question. So it says a student clamped a wire between the poles of a permanent magnet. The student investigated how the force on the wire varied with the current in the wire. The diagram shows the equipment used. So we've got a top pan balance here, and it says that this was used to determine the force on the wire, and when the switch was closed, the reading on the top pan balance increased. Explain why the increased reading showed there was an upward force on the wire. So this is an example of the motor effect, which I'm not going to go into the details of precisely how it works now. But effectively, when this wire carries current, it has its own magnetic field, which is going to interact with the magnetic field of the permanent magnet. And then there's going to be, that interaction is going to lead to a force acting on the wire because of the way those different magnetic fields are going to repel, attract each other. And so it says here that when the switch was closed, the reading on the top pan balance increased. If the reading on the top pan balance has increased, the reason for the reading increasing is because of the fact that there is a downward force pushing that magnet down. So that magnet has got to be experiencing a downward force onto the top pan balance. That's going to cause the increase in the reading. If there is a downward force on the top pan balance caused by the wire pushing on the magnet, the wire is also having its own equal and opposite force acting upwards. And that's an example of Newton's third law, that where you've got one object putting a force on another object, that object will put the same type of force back on the previous one, which is equal and opposite in direction. So if the wire is having a force is pushing a force down on the magnet, which is why the top pan balance increases in mass, then the magnet will also push upwards on the wire in an equal and opposite way. So that's why it's an equal force and it's upwards, because it's equal and opposite. Part B. We've then got the readings on the top pan balance, both when the switch is open and switch is closed. And so what we can do there is we can use those data points to be able to calculate the force. So the first step is to work out the change in mass. So we've got 254.8 minus 252.3, which equals 2.5 grams. So 2.5 grams is the difference in mass reading as a result of that force pushing the magnet down. We can convert this into a force by using our knowledge of one of the equations from the worksheet. So let me just find it for you. There we go. It was on that page already. So weight is equal to mass times gravitational field strength. Weight is the force that we're going to be able to calculate here. So we need to turn that mass into a force. And the way that we're going to do that is we're going to times it by the strength of gravity. And as I earlier said to you, 9.8 is the typical value that we would use for the strength of gravity. So I can work out this by doing mass times 9.8 is equal to our force. Now, my mass is 2.5 grams. The problem with this is in grams, and mass is normally measured in kilograms. So 2.5 grams is actually 2.5 over 1,000, so 0.0025 times 9.8. Again, I can't do that in my head, so let me just do that quickly. So I've got an answer now of 0.0245. Okay, so that is how we'd calculate that one. And then the last one we've got here is an example of a fairly complex calculation, which is utilizing this very bottom equation on the equation sheet, which is to do with something called magnetic flux density. Magnetic flux density is a measure of effectively the strength of a magnetic field. And what we can do is there is an equation that links the force on a conductor, which is within a magnetic field, like a piece of wire that's being used in the example of this question. And that force is dependent on the magnetic field strength, the magnetic flux density, the current flowing through the conductor, and also the length of the conductor that is in the magnetic field, whereby force is equal to flux density times current times length. And what we've got here is some information about the students' calculations whereby they have done this experiment with the wire inside the magnetic field, and they have effectively changed the current that is flowing through the wire, and for each of those different currents they have then converted it, they've calculated the force by doing what we were going through for part B. They've then plotted this data on a graph, and they have then kind of illustrated it here with a line of best fit. And we're told one extra bit of information that I'm just going to highlight, which is that the length of the wire, sorry, the highlighter seems to have stopped working, so I'll just underline it. The length of the wire is 0.125. So what I'm going to do is I'm going to type out that equation from the equation sheet. And again, this is about you looking at what is it I need to know, which in this case is the magnetic flux density, and going back to the equation sheet and finding that equation. So force is flux density times current times length. And what we're trying to work out is the flux density. So I'm not going to try and completely rearrange this just yet. What I'm going to do is I'm going to do a partial rearrangement at the beginning. And what I'm going to do is I'm going to get rid of the current. So to, if you like, get rid of the current from the right hand side. At the moment it's being times by current. So therefore I need to divide. So force divided by current is equal to the flux density times by the length of the wire. Now we actually know the length of the wire because of the fact that it's given to us as 0.125. So I'm just going to do force over current equals flux density times 0.125. We also know force times current. And the reason we know this is because we have a plot of points on our graph here of how the force changes with current. Now we can't just pick any 2 points from the graph. We're going to use our line of best fit instead, and we're going to work out the gradient of that line of best fit, which is representing that whole set of data. And to work out the gradient, you need to do the change in y divided by the change in x. So using some of those skills I mentioned earlier about using a ruler to draw really accurately and read really clear points from it, I'm going to take a point on the graph and I'm going to, from that point, turn it into a triangle, and over that time work out what was the change in y, the change in the force, what was the change in x, the change in the current. And if I'm doing force over current, that's equivalent to this other unknown in my equation. So I'm going to take the point where I can see the line really nicely intersecting, ideally as much as possible, through a clean square. So I'm going to go at this point here. So I'm going to try my best, and apologies again for the wobbly line, but that's going to go there. And then if I go down, ooh, that was terrible. It's going to go there. Now, don't fall into the trap of at that point going, oh, it's this number on the y-axis, it's this number on the x-axis. Because if we look, the line does not start at 0. So it's very important we don't assume it has. So the force change here, if it's 0.0150, and then there's 5 squares up to 0.020, and again, just watch out there for that 0.0. This is going to be 0.0180. And that is going to be the change, because if we look at the beginning of our little triangle, the force was at 0 at the beginning. The current change, though, is at 0.6 amps on the right-hand side. On the left-hand side of the triangle here, actually it's crossed over after 1 square, which is equivalent to 0.02, because of the fact that there are 5 squares between 0 and 0.1, so each square is worth 0.02. So this actually becomes 0.018 divided by 0.02. Sorry, 0.02, 0.58. Apologies, we're doing the difference between 0.6 and 0.02, so that's why it's 0.58. That then is our gradient, so that's me putting those numbers in there. And then that's going to be equal to our flux density times by 0.125. So let's do a bit of calculations. So 0.018 divided by 0.58 is equal to 0.31. 0.031, apologies. And that is equal to the flux density times 0.125. And then I can do 0.031 divided by 0.125 equals the flux density. So I have then got an answer of 0.25. And the unit for that is Tesla, but it is actually given to you in the question. So that again would be an example of a pretty challenging calculation, because you've got to work at a gradient and you've got to be careful about the axes on the graph there, but hopefully you can now see where those numbers have come from. Thank you very much.